10.1 Sequences. The outline of this video is as follows. First, we will explore different ways to represent sequences, which are ordered lists of numbers. This includes looking at them graphically. Next, we will introduce the core concepts of convergence and divergence. This is the central idea for determining whether a sequence approaches a specific finite value as we go further and further out. After that, we will learn about several common and important limits that frequently appear in problems. Knowing these will save you a lot of time. Finally, we will discuss two special properties of sequences: being bounded and being monotonic. These properties will help us determine if a sequence converges, even when calculating the exact limit is difficult. Let us formally define a sequence. A sequence is an ordered list of numbers, where each number's value often follows a specific mathematical rule. Each number in the list is called a term, and the integer n that marks its position is called the index. For example, a sub 2 is the second term in the list. A powerful way to think about this is to view a sequence as a function. This function takes a positive integer n as its input and outputs the nth term of the sequence, a sub n. Let us look at the examples to see this in action. For the sequence of even numbers 2, 4, 6, 8, and so on, the generating function is a sub n equals 2 times n. Plugging in n equals 1 gives the first term, 2, and n equals 2 gives the second term, 4. The second example shows an alternating sequence whose rule is b sub n equals -1 to the power of n plus 1, all divided by n. The main takeaway is that a sequence is just an ordered list of numbers, typically defined by a formula based on the term's index. To better understand the behavior of a sequence, it is helpful to visualize it graphically. There are two common ways to do this. The first method is to simply plot the terms as points on the real number line. This shows the distribution of the values, but it hides the order in which the terms appear. A more informative method is to plot the sequence as a set of points in a two-dimensional Cartesian plane. For this type of graph, the horizontal axis represents the index, an, which takes on integer values like 1, 2, 3, and so on. The vertical axis represents the value of the corresponding term, a sub n. For instance, for the sequence where a sub n equals 1 over n, the graph would consist of the discrete points 1, 1, 2, 1/2, 3, 1/3, and so on. Remember, this is a graph of isolated points, not a continuous curve, because the index n is an integer. This two-dimensional plot is especially useful for seeing the long-term trend of a sequence and whether it approaches a specific value. This slide presents the formal definition of what it means for a sequence to converge to a limit. This definition captures the idea that the terms a sub n get arbitrarily close to a number L and then stay that close. It works like a challenge. For any small positive tolerance you choose, called epsilon, there must be a point in the sequence, an index n, after which all subsequent terms are within that epsilon distance of L. The expression, the absolute value of a sub n minus L is less than epsilon, simply states that the distance between the term and the limit is smaller than your chosen tolerance. The key is that we must be able to find such an n for any positive epsilon, no matter how small it is. If no single number L exists that satisfies this condition for every possible epsilon, we say the sequence diverges. When a limit L does exist, we use the notation shown and call L the limit of the sequence. Let us translate the formal definition of convergence into a more intuitive, graphical picture. This visualization is key to understanding what it means for a sequence to approach a limit. The small positive number, epsilon, creates a horizontal band or corridor around the potential limit, L. The top edge of this band is at y equals L plus epsilon, and the bottom edge is at y equals L minus epsilon. You can make this band as narrow as you like by choosing a smaller epsilon. The definition guarantees that no matter how narrow you make that band, you can always go far enough out in the sequence to some index n such that all subsequent terms lie entirely inside it. A few early terms might fall outside, but after the nth term, the sequence is permanently trapped within that epsilon corridor. This is precisely why we say the line y equals L acts as a horizontal asymptote for the sequence. The points representing the sequence get and stay arbitrarily close to this line as n gets very large. Let us apply the formal definition of a limit to see how it works, with a few key examples. First, for the sequence 1 over n, we can prove that the limit is 0. For the terms to stay within some small distance epsilon of 0, the index n must be larger than the quantity 1 over epsilon. Since we can always find an integer n that satisfies this condition for any epsilon, the limit is 0. For a constant sequence k, the logic is even more direct. The distance between any term and the limit k is always 0, which is less than any positive epsilons. In contrast, the sequence that alternates between +1 and -1 diverges. Its terms perpetually oscillate between two values and never settle down to get arbitrarily close to a single, unique number, no matter how far out we go. These examples provide a concrete look at how the formal definition rigorously separates convergent sequences from divergent ones. Let us now formalize the idea of a sequence whose terms grow without any bound. This is what we call divergence to infinity, and this slide provides the precise mathematical definition. You can think of this definition as a challenge. For any large number you can possibly name, which we call m, I can always find a point in the sequence, an index n, such that all the following terms are guaranteed to be larger than your number, m. For example, with the sequence a sub n equals n squared, if you choose m to be 1 million, I can just point to n equals 1,000. Every term after that point is larger than 1 million. This same logic works in reverse for a sequence that diverges to negative infinity, where its terms eventually fall below any negative number. It is important to remember that this is a specific type of divergence. A sequence can also diverge by oscillating, without ever approaching positive or negative infinity. The key takeaway is that divergence to infinity means the sequence's terms must eventually exceed and stay above any finite boundary. This theorem provides a powerful toolkit for calculating limits, known as the limit laws for sequences. The main idea is that if you start with sequences that you already know are convergent, you can find the limits of their arithmetic combinations. Let us say the sequence a sub n converges to a limit a, and the sequence b sub n converges to a limit b. The sum and difference rules tell us that the limit of their sum or difference is simply the sum or difference of their limits, a plus b or a minus b. Similarly, the product rule shows the limit of their product is a times b. The quotient rule follows the same pattern, giving a over b, but with the important requirement that the denominator's limit, b, cannot be 0. Finally, the constant multiple rule states that you can factor any constant k out of a limit. These laws are incredibly useful, but remember, they only apply if the initial sequences converge. In short, limits behave predictably with respect to addition, subtraction, multiplication, and division. We can now combine the algebraic limit rules with our known basic limits to evaluate more complicated sequences. These examples demonstrate how the sum, difference, product, and quotient rules are applied in practice. In the first case, we use the constant multiple rule. The limit of -1 over n is simply -1 times the known limit of 1 over n, giving us a result of 0. For the second example, we first rewrite the fraction as 1 minus the quantity 1 over n. Applying the difference rule, the limit is 1 minus 0, which equals 1. The third example uses both the constant multiple and product rules. The limit of 5 over n squared is 5 times the limit of 1 over n, multiplied by the limit of 1 over n again, resulting in 0. Finally, for the rational expression, we use a standard technique. Divide the numerator and denominator by the highest power of n, which is n to the power of 6. After this step, the terms with n in the denominator approach 0, leaving a final result of -7. Now let us look at a very intuitive but powerful result called the sandwich theorem for sequences. This theorem provides a clever way to find the limit of a sequence that might be difficult to calculate directly. The main idea involves 3 sequences. Suppose we have a sequence, which we can call b sub n, whose limit we want to find. If we can find 2 other sequences, a sub n and c sub n, that effectively trap or sandwich our sequence, we can use their behavior to understand b sub n. The conditions are straightforward. First, for all terms eventually, the sequence a sub n must be less than or equal to b sub n, which in turn must be less than or equal to c sub n. Second, and this is the key, the 2 outer sequences, a sub n and c sub n, must both converge to the exact same finite limit, which we will call L. If both of these conditions are met, the conclusion is simple. The sequence b sub n, being squeezed between the other 2, is forced to converge to that same limit L as well. Let us apply the sandwich theorem to a few common examples. This theorem is a powerful tool for finding the limits of sequences that have bounded terms, such as those involving trigonometric functions. First, consider the sequence cosine of n divided by n. We know the cosine function itself is always bounded between -1 and +1. This means our sequence is always sandwiched between -1 over n and +1 over n. Since both of these bounding sequences go to 0 as n goes to infinity, our original sequence must also converge to 0. Next, consider 1 over 2 to the power of n. This term is always greater than 0. It is also less than or equal to 1 over n for all n greater than or equal to 1. The sequence is therefore squeezed between 0 and 1 over n, forcing its limit to be 0. Finally, the alternating sequence, -1 to the power of n over n, is bounded between -1 over n and +1 over n. Just like in the first example, both of these outer sequences go to 0, so the sequence caught between them must also converge to 0. This theorem provides a powerful tool for finding the limits of new sequences, especially when they are formed by applying a function to a sequence whose limit we already know. The continuous function theorem states that if a sequence, a sub n, converges to a limit L, and you apply a function f that is continuous at L, then the new sequence of function values, f of a sub n, will converge to f of L. Essentially, this means you can pass the limit inside a continuous function. Let us look at the first example. We know that the sequence given by the quantity n plus 1 all over n converges to 1. Since the square root function is continuous at x equals 1, the theorem tells us that the square root of our sequence converges to the square root of 1, which is just 1. Similarly, for the second example, the sequence 1 over n converges to 0. The function f of x equals 2 to the power of x is continuous at x equals 0. Therefore, the sequence 2 to the power of 1 over n must converge to 2 to the power of 0, which also equals 1. The key takeaway is that continuity allows us to exchange the order of applying a function and taking the limit of a sequence. We now have a very powerful theorem that formally connects the limit of a sequence to the limit of a continuous function. This is incredibly useful because it allows us to use tools from calculus, like L'Hopital's rule, to analyze sequences. Theorem 4 states that if we can find a function, f of x, that matches our sequence at every integer n, and the limit of that function as x approaches infinity is some value L, then the limit of the sequence a sub n is also L. Let us see this in action. We want to find the limit of the sequence given by the natural log of n, all over n. The corresponding function is f of x equals the natural log of x over x. As x approaches infinity, this gives the indeterminate form, infinity over infinity, so we can apply L'Hopital's rule. The derivative of the numerator is 1 over x, and the derivative of the denominator is 1. The limit of the resulting fraction, 1 over x, is 0. Because the limit of the function is 0, Theorem 4 guarantees that the limit of our original sequence is also 0. Let us tackle a common but tricky indeterminate form, 1 raised to the power of infinity. We can solve this by first taking the natural logarithm of the sequence term, which allows us to apply L'Hopital's rules. Our sequence is the quantity n plus 1 over n minus 1, all raised to the nth power. As n gets large, the base approaches 1 while the exponent goes to infinity. The key step is to analyze the natural log of our term, a(n). This brings the exponent n down as a multiplier, giving us n times the log of the fraction. This expression now has the form infinity times 0. To use L'Hopital's rule, we rewrite this as a quotient, the log term divided by the quantity 1 over n. Now we have the form 0 over 0. Applying L'Hopital's rule and simplifying the resulting fraction shows that the limit of the natural log of a(n) is equal to 2. It is crucial to remember this is not our final answer. Since the limit of the logarithm of a(n) is 2, and the exponential function is continuous, the limit of the original sequence a(n) must be e raised to the power of 2. Therefore, the sequence converges to e squared. This theorem provides a toolkit of 6 very common and useful limits. Knowing these will make it much easier to determine the convergence of more complicated sequences you will encounter later. The first limit shows that n grows much faster than the natural log of n, so their ratio goes to 0. The second and third limits are related. The nth root of n and the nth root of any positive constant x both approach 1 as n goes to infinity. The fourth limit is for a geometric sequence, x to the power of n. It converges to 0 as long as the absolute value of x is less than 1. The fifth limit is a fundamental definition of the exponential function. The quantity 1 plus x over n, all raised to the nth power, converges to e to the x. Finally, the sixth limit shows the power of the factorial function for any x. The fraction x to the n over n factorial goes to 0, because n factorial grows faster than any exponential function. The main idea here is to understand the hierarchy of growth rates for these common functions. Instead of calculating each term directly from its index n, we can define a sequence recursively. This method builds the sequence step by step, where each new term depends on the ones that came before it. To do this, we need 2 things. First, the value of the initial term or terms to start the process, and second, a rule called a recursion formula to find any later term from its predecessors. For example, the positive integers can be defined by starting with a sub 1 equals 1, and then using the rule that a sub n equals the previous term, a sub n minus 1 plus 1. The sequence of factorials also starts with a sub 1 equals 1, but its rule is that a sub n equals n times the previous term, a sub n minus 1. The famous Fibonacci sequence requires 2 starting terms, a sub 1 and a sub 2 both equal to 1. Its rule states that any term after the second is the sum of the two preceding terms. In short, recursive definitions provide a starting point and a step-by-step recipe for generating the rest of the sequence. Let us establish the concept of a bounded sequence, which is a necessary, but not sufficient, condition for convergence. A sequence is bounded from above if there is a number, m, called an upper bound, that is greater than or equal to every term in the sequence. Likewise, a sequence is bounded from below if there is a number, m, a lower bound, that is less than or equal to every term. If a sequence has both an upper and a lower bound, we simply call it a bounded sequence. Now for the most important fact on this slide, if a sequence converges to a limit, it must be bounded. This makes intuitive sense, as a sequence approaching a single value cannot also be heading toward infinity. However, the reverse is not true. Being bounded does not guarantee convergence. For example, the sequence given by the quantity -1 to the power n simply alternates between -1 and +1. It is bounded, but it never settles on a single limit. So, the essential result is that convergence implies boundedness, but boundedness does not imply convergence. We will now define a key property for sequences called monotonicity. This property describes sequences that consistently head in one general direction, which is a crucial feature for determining convergence, especially when combined with boundedness. A sequence is called non-decreasing if every term is greater than or equal to the one before it. In other words, the terms never get smaller. Conversely, a sequence is non-increasing if every term is less than or equal to the one before it, meaning the terms never get larger. A sequence is called monotonic if it is either non-decreasing or non-increasing. It is important to note the or equal to part of these definitions. A non-decreasing sequence can have terms that stay the same. It just cannot go down. For example, the sequence of integers 1, 2, 3, and so on is non-decreasing. The sequence 1, 1/2, 1/4, and so on is non-increasing. However, a sequence like 1, -1, 1, -1, which alternates up and down, is not monotonic because it does not stick to a single direction. In short, a monotonic sequence is one that never reverses its overall direction of travel. We now arrive at a powerful result that connects the ideas of boundedness and monotonicity. The monotonic sequence theorem provides a simple condition that guarantees a sequence will converge. The theorem states that if a sequence is both monotonic, meaning it only moves in one direction without reversing, and bounded, meaning it is confined between some upper and lower values, then that sequence must converge to a limit. This breaks down into two key scenarios. A non-decreasing sequence that is bounded from above cannot grow to infinity, so it must converge. Its limit will be its least upper bound. Likewise, a non-increasing sequence that is bounded from below cannot fall to negative infinity, so it must also converge, and its limit will be its greatest lower bound. For example, the sequence 1/2, 2/3, 3/4, and so on is non-decreasing and is always less than 1. The theorem guarantees it converges to its least upper bound, which is 1. In short, a monotonic sequence that is trapped by a bound must settle on a specific limiting value. Let us summarize the key ideas we have discussed about sequences. We started by defining a sequence as an ordered list of numbers and introduced the fundamental concept of convergence. The sequence converges if its terms approach a single limiting value. Otherwise, it diverges. We saw that the standard limit laws for sums, products, and quotients apply directly to sequences, making many calculations straightforward. For more challenging cases, we developed a powerful toolkit. This includes the sandwich theorem for trapping a sequence, the continuous function theorem for applying functions to limits, and the use of L'Hopital's rule. Finally, we have the monotonic sequence theorem. This is a crucial result which guarantees that a sequence must converge if it is both bounded and monotonic, meaning it is consistently increasing or decreasing. These concepts are the foundation for our next topic, infinite series. Let us work through a final example using L'Hopital's rule. We want to find the limit of the sequence. A sub n equals n times the quantity e to the power of 1 over n minus 1. As n approaches infinity, this becomes the indeterminate form, infinity times 0. To handle this, we can rewrite the sequence as a fraction by moving n to the denominator. This gives us the expression e to the power of 1 over n minus 1, all divided by 1 over n. Now, as n goes to infinity, we have the 0 over 0 form. To make the differentiation clear, let us substitute x for 1 over n. The problem is now to find the limit of the quantity e to the x minus 1 all over x as x approaches 0. Applying L'Hopital's rule, we differentiate the top and bottom with respect to x. This gives us e to the x in the numerator and 1 in the denominator. The limit of e to the x as x approaches 0 is simply e to the 0, which is 1. Therefore, the sequence converges to a limit of 1.